Hello?
Okay, yeah.
Yeah, okay. So I'll just share my screen just a minute. So this is your assignment, right? If I'm once again. Is my screen visible?
Yes.
This is your assignment, right?
Yes.
Okay, so first of all, let me just ask you uh, do you have any doubts, like generally, conceptually?
Yeah, I have one doubt.
Hmm.
When the Hessian matrix, no, if it has a negative and a positive eigenvalue,
Hmm.
then what sir has said is we take something called Z transport Hessian matrix Z and we compute the positive definiteness of this matrix.
See the positive definiteness. There's a shortcut to find that. Just find the eigenvalues. Okay. So if the eigenvalues are all positive, then it's surely a
Positive and all
minimum.
negative is okay. When it is one positive, one negative, when it is a
Then,
saddle.
then it is neither a maximum nor a minimum. It's called a saddle point. Okay. It's neither a maximum nor a minimum. Its technical name is saddle. Okay.
Yeah. But sir, what he did know in the equality constraint condition, when a condition to minimize a function is given, and then once a equality is given, the constraint set has a equality. And once we calculate the Hessian matrix, and if it is coming as one eigenvalue negative and one positive, then he said key to check for the positive definiteness of this matrix, what we need to do is we find the null space of a D vector.
Okay. Okay.
That case
Okay.
I
Okay.
was getting
So
confused.
I don't think so. This is for a constrained optimization with equality constraint, a second order test, right? Hessian.
Yes.
So like most probably you don't need to do that because if you just check the first order condition, you will get a bunch of points, right?
Correct. Correct.
You can simply check which of them is the minimum among them or which of them is the maximum among what you have gotten. Okay, you don't need to do second order test as such. Yeah. But in case you need to do it, then as you said, you have the null space and then check restricted to the null space. You have to check whether the matrix is
But
positive
the
definite or not.
problem is if there are two equality constraints, so he said like a delta of H we take it.
Okay, so I don't know exactly what he did. Wait, this is is
I,
this the presentation that he used? Just a minute.
if I can share my screen, I can. I have paused it on the video slide.
Okay, you can share your screen.
So is the screen visible?
Why is the Hessian coming here?
Yes, yes, yes. See, 1 minute.
Because I don't remember Hessian computation for constrained problems. That's why I'm asking.
Just also, just give me a minute. Sorry. In 1911. Maybe I'll come back. Give me a minute. I just.
Yeah, so keep it ready. What I thought of was I'll solve the first problem completely. That will be a good demo, okay? and then you can, and then I'll tell you if you have any other doubts, I'll tell you the hints for any problem that you may have doubts on. Okay, is that fine? So shall I share my screen again?
Yes, please.
So I will solve the first problem completely. Just so this was your problem, right? The first two bullet points, that's your question, right? Can you see it? Hello?
Yes.
Yes.
So I will just recap the KKT conditions, which you might have already seen. So just a minute. This. Okay, I think. So these are the KKT conditions. Do you remember? So the first condition is the gradient condition. So the gradient of f should be a linear combination of gradient of the constraint function c, ci, and lambda I is called the Lagrange multiplier. This is familiar? And then what you have is lambda I should always be non-negative, and ci of x should be non-negative. Ci of x being non-negative is the constraint, and lambda I being non-negative is the Lagrange multiplier. And the thing is, one of them should be 0. Okay, so either lambda I should be 0 or Ci should be 0 for each constraint I. For inequality constraint, it's called complementary slackness. So for inequality constraints, you need complementary slackness. Okay, which means either lambda I has to be 0 or Ci has to be 0. Both of them cannot be non-zero. Okay, so those are the complementary slackness condition. So we will just so this is f of x, correct? Now this is g1 of x, the first constraint, x1 minus 80, that should be greater than or equal to 0. This is the second constraint, g2 of x, which is x1 plus x2 minus 120 greater than or equal to 0. So the first two lines are clear, right? First two bullet points is basically the question. I'm just reformulating the question in terms of standard form. And then I'm computing gradient of f, gradient of g1, gradient of g2. Are the gradients clear? You have to respond, otherwise I don't know whether you're following or not. Somebody has to respond.
Yes, yes. So we have
So for
taken first.
gradient of f, you have to take the partial with respect to x1 for the first entry and partial with respect to x2 for the second entry. So if you take the partial with respect to x1, you will get x1 square, the derivative is 2x1, and then 60x1, the derivative is 60, so 2x1 plus 60. The partial of second with respect to x2 is just 2x2. x2 square's derivative is 2x2, that's it. And g1 and g2 are linear functions, so the gradients will be constant. So g1 is x1 minus 80, the partial with respect to x1 is 1. It doesn't depend on x2, so the partial with respect to x2 is 0. And for g2, it is x1 plus x2, right? So the partial for x1 is 1, the partial for x2 is also 1. Up to this, is this clear? Got it?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes.
So there are two inequality constraints here. So there are two Lagrange multipliers, lambda 1 and lambda 2. So now I told you, right? Either lambda 1 has to be 0 or, G1 has to be 0 at the optimum. Correct? It's complementary slackness. But the thing is, you don't know, what is what. So you have to consider all four cases. So there are four cases here. First case is both lambda 1 and lambda 2 are 0. Okay, that is one possibility. So in that case, G1 and G2 will be non-zero. The second possibility is lambda 1, lambda 2 both are non-zero, in which case G1 and G2 both are 0. So here we have both constraints active. The third case is one of them is, active, which is lambda 1 is positive and G1 is 0. Whereas for the other constraint, lambda 2 is 0, but G2 is non-zero. The last case is the first constraint, we have G1 is non-zero and lambda 1 is 0. And the second constraint, we have G2 is 0 and lambda 2 is non-zero. Are these four cases clear?
Yes, sir.
So you have to solve for each four case separately, okay? And then you have to verify whether the solution is making sense or not. So I'll take the first case where I assume both lambda 1 and lambda 2, both of them are 0, in which case G1 and G2, both of them should be non-zero. So G1 and G2, if it is non-zero, have to be positive because the constraint is that G1 and G2 are greater than or equal to 0. So if it is not equal to 0, then it has to be greater than 0. And this is the gradient condition. So gradient of f should be lambda 1 gradient G1 plus lambda 2 gradient G2. Here lambda 1, lambda 2 both are, I'm assuming to be 0. So it's just 0 plus 0 is equal to 0. So you just have gradient of f is equal to 0. So when you equate gradient of f is equal to 0, you just get 2x1 plus 60 equal to 0 and then 2x2 is equal to 0. So you get x1 is equal to minus 30 and x2 is equal to 0. Is it fine? Is this fine?
Yes,
So in
yes,
this case,
yes.
you are just solving the unconstrained problem and then you are equating the gradient to 0. But the thing is, you got a solution now, minus 30 comma 0, but you have to see whether it satisfies both the constraints or not. Otherwise it is out. Because because G1 and G2 have to be positive, right? So substitute x1 is equal to minus 30 and x2 equal to 0. Check whether G1 and G2 both are positive. And here you see it is not positive. It is coming negative. So G1 is coming negative. So it's out. So this solution is out. So this case one is impossible because it throws a stupid solution, which is not feasible at all. Got it? Is this case clear?
Yes, sir.
Now in case 2, what you assume is, you assume both of them are lambda 1, lambda 2, both are positive, non-zero, but so by complementary factors, G1 and G2, both of them have to be 0. Okay. So this is the KKT condition. The gradient of f should be lambda 1 gradient G1 plus lambda 2 gradient G2. And if you substitute the expression for gradient G1 and gradient G2, and then if you add them all, you will get whatever I have shared in blue. Is this fine?
Sir, one doubt here.
So because this is basically lambda 1 times 1 0. So lambda 1 times 1 0 plus lambda 2 times 1 1. Correct? Lambda 1 times 1 0 plus lambda 2 times 1 1, which will give you lambda 1 plus lambda 2 and then lambda 2. Got it?
Sir, one doubt
Got
here.
it? Yeah.
Sir, in some places people are putting negative symbol before lambda. So in some Lagrangian equation, in some they are putting plus. So
Okay, it all depends on whether you formulate the problem as a positive constraint or negative constraint, whether you assume G1 is greater than or equal to 0 or G1 is less than or equal to 0, depending on that. Okay.
Okay.
So that should not be a problem. Okay. If G1 and G2 are formulated as a negative constraint, then the signs for lambda 1, lambda 2 will change. Okay. Got it?
Okay. Yeah, okay. Got it. Thanks.
But sir taught you this only, right? Since I am newly appointed, sir just sent me the PPT. I see only this. So that's
Yes, sir.
why I assumed this. Okay.
Yeah.
So in other textbooks, you may find other things depending on whether you write as a minimum or a maximum, depending on whether you have G1, G2 positive or negative, it will get changed. So now if you equate, so you have to equate the component wise, 2x1 plus 60 should be equal to lambda 1 plus lambda 2. If you do that, you get the equation 3 that I have written here. 2x1 plus 60 minus lambda 1 minus lambda 2 is equal to 0. Now, if you equate the second component, 2x2 should be equal to lambda 2. So that if you write, you get equation number 4. So you have now 4 unknowns, x1, x2, lambda 1, lambda 2, but you have only 2 equations. The remaining 2 equations will come from the constraints because I'm assuming G1 is equal to 0, G2 is equal to 0. So G1 is basically x1 minus 80, that should be equal to 0. G2 is basically x1 plus x2 minus 120, that should be equal to 0. Okay. So you have 4 equations and 4 unknowns. So this is a simple problem. You don't even need to do linear algebra. You can just substitute. Equation 5 gives x1 is equal to 80. And then if you substitute x1 is equal to 80 in equation 6, you get x2 is equal to 40. And then if you substitute for x2 equal to 40 in equation 4, you get lambda 2 is 80. And if you substitute for x1, x2 and lambda 2 in equation 3, you get lambda 1 is 140. So you have now x1 is 80, x2 is 40, lambda 2 is 80 and lambda 1 is 140. Is this clear? So now what you have to do is you have to check if lambda 1 and lambda 2 are indeed positive. They are indeed positive. You get lambda 1 is 140 and lambda 2 is equal to 80. They are indeed positive as you assumed. So this makes sense. So this x1 is equal to 80 and x2 equal to 40 is in. It's a candidate solution for the optimum. Okay. So this is in. It is acceptable. That's what I am written on the bottom. It satisfies all the assumptions in the KKT conditions. So it is acceptable. Got it? Got it?
Sir, in this
Yes, sir.
case, we don't need to check for G1 and G2 conditions, right? Because from there only we arrived at x1 equals to 80 and x2 equals to 40.
Yeah, I already assumed G1 is equal to 0 and G2 equal to 0, right? The original constraint was G1 and G2 are greater than or equal to 0. But since you are assuming the constraint to be active, you already equated them to 0, correct?
Okay.
So you just need to check the lambda case. If you assume lambda equal to 0, you have to check whether G is positive. If you assume G is equal to 0, you have to check whether lambda is positive. Okay.
Okay. Okay.
So if you assume one of them to be 0, the other you have to check whether it is positive or not. If it is positive, then that solution is acceptable. If you assume lambda 1 is 0, you have to check whether G1 is positive or not. If you assume G1 is equal to 0, you have to check whether lambda 1 is positive or not. Okay. Now case 3. Here what we assume is we are assuming lambda 1 is positive, which means G1 is equal to 0, complementary slackness. And then we are assuming lambda 2 equal to 0, which means G2 is positive. We are assuming this. So now again, this is the gradient of F. Nothing will change. Again, G1, G2 gradient, nothing will change. But here, since you are assuming lambda 2 equal to 0, you will have only lambda 1 times 1, 0, which is lambda 1, 0. Got it? The second term will be 0 because you are assuming lambda 2 equal to 0 here. So now if you equate component wise, if you equate 2x plus 1 plus 60 is equal to lambda 1 here, you get equation 8, which is here. Okay. And then if you equate 2x2 at the bottom here, if you equate this to 0, you get 2x2 equal to 0 in equation 9. So here there are 3 unknowns, x1, x2 and lambda 1. You need one more equation. So for that you have G1 is equal to 0. So x1 minus 80 should be equal to 0. So you get 3 equations. So now if you solve them, you get x1 is equal to 80, x2 equal to 0, and you get lambda 1 is 220. So your lambda 1 is positive, so that makes sense. But we have to check whether G2 is positive or not, because that's what you assumed, right? If G2 is non-zero, I have assumed it has to be positive, it cannot be negative. So you put x1 is equal to 80 and x2 equal to 0 in G2. What you get is that you have x1 plus x2 minus 120 is 80 minus 120, which is minus 40, which is not positive. So this solution is trash, garbage. It has to be thrown out because it doesn't satisfy one of the constraints. Got it? Okay. Is this fine?
Yes, sir.
Now the last case, here the ulta, you assume lambda 1 is equal to 0, and then you assume lambda 2 is positive, which means G1 will be positive and G2 equal to 0. Whatever is 0, the other one you assume to be positive. Again, KKT conditions, that here you will have lambda 1 is equal to 0 and lambda 2 you will come as such. So lambda 2 times gradient of G2, gradient of G2 is 1, 1 we saw. So you will just get lambda 2, lambda 2. So equate component wise, you get 2x1 plus 60 is equal to lambda 2. That is equation 13 here. Equation 14 will be 2x2 is equal to lambda 2. If you rewrite that, you will get 2x2 equal to lambda 2. And then for the other equation, you'll have G2 equal to 0, which means here x1 plus x2 minus 120 is equal to 0. Got it? So now if you solve this, you'll get x1 is 45. So this is a little bit substitution you have to do. If you solve it, you'll get x1 is equal to 45, x2 equal to 75, and lambda 2 is 150. So lambda 2 is positive, that is okay. But let's see if the other constraint holds, if G1 is indeed positive. So substitute x1 is equal to 45 and x2 equal to 75 in G1. G1 is x1 minus 80, 45 minus 80, which is minus 35, which is not positive. So again, the first constraint is not satisfied with the solution. So the solution has to be eliminated. It is trash. Okay. So out of the 4 cases that we assume, there is only one that satisfies all the conditions, which is case 2, correct? Only this is acceptable. So that has to be the optimal point. The thing
Sir,
is,
here
if you have more than one solution satisfying KKT, then what you do is you check where the objective function is least, and that should be the minimum. Okay, got it? Got it?
By objective function, you mean f.
Yes, yeah. You substitute x1 is equal to that thing, x2 equal to that thing. F value you check. Out of all the candidate solutions which are acceptable in all then you check which one of them makes f the least. Like in function of one variable which is without any constraint, you equate the first derivative to 0, and then you get a bunch of values. Then if you want to check which is the minimum, then you will substitute them and see where f is the least, right? Same thing.
Okay.
Here you get only one case acceptable and all the 3 are trash. So no problem, that has to be the solution. But in case if you have more than one case giving solution, let's say you have 2 acceptable solutions from 2 cases, then substitute x1 is equal to the x1, x2 values from both of them. Check which one of them has lower value for f. Okay. So that one has to be the solution. So that is so everything is like this. So for inequality conditions, you have to argue case wise. For equality condition, if you remember, there is no constraint on the sign of lambda. So G has to be 0 for the equality condition always. That's the definition. G has to be equal to 0. So and lambda can be positive or negative, doesn't matter. So that for equality constraint. For inequality constraint, you have to argue case wise. For example, if you look at the second problem, you have all equality constraints. So you just need to, you don't get any case here. You just have only one case. So you just have gradient of f is lambda 1 gradient g1 plus lambda 2 gradient g2. And then you have g1 equal to 0, g2 equal to 0. And then you just solve them. That's all. Lambda 1 is negative or positive, doesn't matter for equality constraint. But if you have, for example, if you have here 7th problem, for example, minimize x1 square plus x2 square, subject to you have 3 inequality and 1 equality. So what you do here is 3 inequality constraints. So yeah, lambda 1, lambda 2, lambda 3. For the equality case, for lambda 4, don't forget, don't bother about that. It can be either sign. G4 should be 0. So lambda 4 can be either sign. But for if you have 3 cases, how many possibilities you will get? So for 2 inequality constraints, you get 4 cases, right? You have alternatives. Both of them 0, both of them non-zero. First one 0, second one non-zero. First one non-zero, second one 0. So you get 2 square, which is 4 alternatives. For 3 inequality constraints, how many alternatives you will have?
3 factorial.
9.
Yeah, 3, 9. Okay, so because each of them can be either positive or 0, right? Each of them can be 0 or non-zero. Each of the lambdas can be either 0 or positive. So you get 8 possibilities, correct? So lambda 1 can be 0 or non-zero, lambda 2 can be 0 or non-zero, lambda 3 can be 0 or non-zero. So you get 8 possibilities, okay? Correct?
Is it 2 to the power whatever
Yeah, 2 to the
constraints are
power
there?
whatever inequality constraints you have.
Okay.
So you have to check all the 8 possibilities, get 8 solutions, filter the unacceptable solutions, filter the garbage, unacceptable cases. Let's say out of the 8 cases, you have only 2 acceptable solutions. Then find out which of them minimizes, has the least value for Z. So that should be the final answer. Okay. So the everything is procedure is the same for every problem. Depending on the number of inequality constraints, the number of cases will increase. So beyond a point, it becomes intractable to solve by hand. You have to use a computer. You know, that's why you have algorithms. But in principle, this is the step.
Actually,
Got
in
it?
some of the questions, there are 5 equations. Say, suppose example number 5, I think.
Question
So
number
there-
5.
Yeah, so there it comes out to be, I think, means many conditions comes into picture. So
Here, just only 2 inequality constraints, right? You will have only 4 cases, as we saw here. There are only 2 inequality conditions here in question 5. So you just have only 4 cases. So you'll have lambda 1 for the first inequality constraint, lambda 2 for the second inequality constraint. So there are only 4 cases. Lambda 1, lambda 2, both of them 0, both of them non-zero. First one 0, second one non-zero, first one non-zero, second one 0. Everything is the same, except that F, G1 and G2 are different now. So instead of F to be x1 square plus x2 square plus 60x1, you will have here minus 2x1 plus x2 plus 2. And G, if you check here, G you have x1 minus 80 is bigger than or equal to 0. Here you will have what? G will be 1 minus x1 the whole cube minus x2, correct?
correct.
And G2 will be x2 plus 0.25 x1 square minus 1. So the G1, G2 will be different, F will be different. Otherwise, it's exactly the same thing. Okay.
Sir, you mentioned that for equality constant, G1 and G2 should be 0, right? And you mentioned that lambda, there would be only one condition, but lambda 1
So
can take spot.
for equality, if equality constraint you have G equal to 0, then lambda G has to be 0. It cannot be non-zero.
Yes.
So
Yes,
lambda can be either sign. It can be either positive or negative. Doesn't matter.
Is it possible that lambda can be 0?
Yeah, it is possible. It is possible. The thing is, at least one of them has to be 0. For inequality constraint, at least one of them. Either the lambda has to be 0 or the G has to be 0. Both of them can be 0, but at least one of them has to be 0. That's what complementary flatness says.
At least both, and both can be also 0, right?
Yeah,
That's
both
what-
can be 0. That if you are extremely lucky, then you get both of them 0. Okay.
Okay. Got it.
So question number 1, 2, 3. Sorry, question number 1 and 2 are same. 1 I solved it. 2 is same as 1, except that you have
Sir,
3
what will be the
variables instead of
condition?
2 variables.
Sir,
Hmm?
sir, you said
Yeah.
that there will be only one condition checked on this in the second question, right? Because there is an equality.
Second question is all equality constraint, right? You'll have lambda 1, lambda 1 gradient G1 plus lambda 2 gradient G2. Just solve them. That's all. G1, G2 have to be 0. So lambda 1, lambda 2 can be any sign. Okay.
So in this equation, I think there will be 5 variables: x1, x2, x3, h1 or h2. So 5 variables.
X1 or
we need
lambda 1, whatever you call it. Okay.
yeah, lambda 1, lambda 2, x1, x2, x3
Yeah.
to solve it.
Yeah. So the gradient condition will give you 3 equations because it's
Correct.
3-dimensional gradient. And then the constraints will give you 2
Constraint
equations.
equation will give the other 2.
So you'll have 5 equations and 5 unknowns. All of them will be linear equations because the function is quadratic, the gradient will be linear. So, correct. So it will be solvable. Okay. They are all linear equations. Question number 5 is same as 1, except the functions are different. Question number 6 is easy. You just have 2 variables and 1 equality constraint. Question number 7, you have a 2-dimensional problem, but you have 3 inequality and 1 equality constraint. So that is one trick you can use for question number 7. To eliminate the equality constraint. You anyway have x1 plus x2 equal to 2, right? So substitute that in the objective function. Substitute x2 is equal to 2 minus x1 in the objective function. And then rewrite all the constraints for just x1, and then you can solve that. You can solve as a 1-dimensional problem. It will be very simpler. Okay, that's one trick.
Sir, objective function in the sense x minus x2 or x1 square plus x2? square.
Objective function x1 square plus x2 square, but instead of x2, put 2 minus x1.
In the
But
constraint
x1
x1 minus x2
Wherever you
also.
find x2, put 2 minus x1. Use the
Constraint.
equality constraint, and then wherever you put find x2, you put x2 is equal to 2 minus x1, and then you will just have one variable. Okay.
Yeah, so in the equality constraint you are saying, not in the objective function.
In the inequality constraint and the objective
Inequality.
function, put x2 is equal to 2 minus x1. Okay.
Okay, in the both you I need to. Yes, got it. Yeah.
For example, the objective function will be x1 square plus 2 minus x1 the whole square. And then the first constraint will be x1 plus x1 minus of 2 minus x1 should be less than or equal to 1. And then x1 greater than or equal to 0. And then 2 minus x1 greater than or equal to 0. Okay. So
In this
everything
case,
will have
yeah. So in this case, I don't need to worry about that last inequality constraint, that is x2 greater than 0.
it will be one-dimensional condition. Okay. You just need to take derivative equal to 0 and then check which of them satisfies the constraint. That's all.
Okay, sir. Okay, got it.
Same for ninth problem is quadratic. I guess 10th problem also you just have one function and one inequality constraint. So that should be okay. So there are only two cases now. There is only one inequality constraint, and lambda is either positive or 0. So just two cases. So any other question you have clarity? You want some clarity?
All these have to be solved by hand, or we can use computer programs.
I mean, is there anything involving algorithm or something you need to use computer? Otherwise, it's just hand calculation will do. For example, if you have you will understand, I guess. I don't think nothing here requires computation as far as I see.
Okay.
Is that PPT shared with us? Not.
Which PPT?
Solution of question 1.
No, you have to do it. So
Okay.
So that is the solution of assignment. Okay. I thought it's just a examples. Okay.
I'm just doing it to guide you. I'm not supposed to even do this, but I'm just helping you here. Okay, so
No, I thought that similar type of examples are there. Okay, sorry.
similar type, just refer your reference books or textbooks, recommended textbooks. You will find lots of exercises. Or in internet, if you type KKT conditions practice problem, you'll get a lot of them.
Okay, sir. Okay, got it.
If you want, you have to take down now only. If you want this solution, you have to take down now only. I'm not supposed to legally share this. Okay. So.
No, sir. We got this first one. Yeah, thank you.
Yeah. So any other conceptually you have any doubt?
Suppose it is only equality constraints, so then do we really need to use KKT or some other like Lagrange?
Yeah, the same KKT conditions only. Complementary slackness won't be a problem because G has to be 0 anyway. So lambda can be either sign. It can be any sign.
Okay. So that is a
Just find the x's and the lambdas, and any lambda is okay. Ignore lambda. Finding x is the main thing for the equality constraint. If you have only equality constraint.
Okay.
So if you have 5 variables and 3 equality constraint, you will have 5 x's and 3 lambdas. So the gradient condition will give you 5 equations because gradients are 5-dimensional, and then the constraints will give you 3 equations. So you 8 equations, 8 variables. Find only the x's, lambdas. You know it's not important. Okay, anything is okay.
Okay.
Any other question?
The same problems, is it possible to also try out like a gradient descent or some other method?
Gradient descent, wait. Gradient descent, What are algorithms have you been taught? Only gradient descent, right? Or any other algorithm you have been taught?
I think gradient descent does start.
Only
Okay.
that was taught, right? What's your question again?
So I am just suppose we get any optimization problem, what should be our approach, right? Whether we should go for KKT first or
The
a gradient.
standard approach is gradient descent, okay?
Right.
So for unconstrained problem, for constrained problem, the thing is KKT condition will give you the equations, but those equations are a bunch of nonlinear equations, right? And if the if the function is quadratic, okay, it will be linear equations only. If the function is quadratic, then the gradients will be linear, and you will have linear equations. So if the constraints and the function, all of them are only quadratic, or linear, then it will be easy. KKT basically reduces to solving a bunch of linear equations for various cases and checking out. But if the function is not linear, not higher than quadratic, you have complicated functions, then there are, you will study that in an advanced course, okay, how to tackle that numerically. But if the objective functions and constraints are all either linear or only quadratic, there are very good algorithms, for filtering out. The straightforward algorithm is whatever I taught you now. The thing is, the number of cases will be exponentially high. If the number of constraints is n, then the number of cases is 2 power n, right? Correct?
Right.
So 2 power n increases very quickly with n. If you computationally, that should be, you would have learned it in a basic course on computational complexity. So there are some cleverer techniques to, filter out unnecessary cases by intuition, and then, taking only a necessary case. So for example, if the function is linear and the constraints are also linear, you get linear program. There's an algorithm called simplex algorithm. So in simplex algorithm, what you do is you kind of assume that some of the lambdas are 0 and some of them are non-zero. You just assume that something, and then you find the solution, and then you intelligently jump to another case based on what you get in the present case by a nice technique that's called the simplex algorithm. You can check that out.
Yes,
So
sir,
that
sir.
will solve very easily. Even for a quadratic program, you have simplex algorithms, a variation of that. So simplex should be the go-to algorithm for linear and quadratic programs. Okay, you can
Okay.
refer that. Did sir
Yes,
teach
sir.
you simplex?
Yeah, he said the next week he will cover it.
Oh, okay then. So maybe next tutorial we will solve a simplex problem. But for now, this is just the concept. Okay, this is just a theory part. So we are teaching only the conditions and some basic gradient descent problem. Okay. So simplex is the bread and butter of computational optimization. Okay.
Okay, so here in this assignment, we don't have to worry about simplex, right?
Yeah, you just need to manually consider all the cases and solve.
Okay.
And if you can graph the function and reason out, then you can eliminate some cases beforehand itself. That also you can do. For
Okay.
example, in the same problem, if I graph the function f of x, if I know the level sets, so there will be ellipses, right? If I can complete the square and then I'll have some square expression, and then if I graph the constraints, if I graph the feasible region, then by seeing the graphs, you will kind of understand, intuitively in which case is the minima has to be. For example, if this is the PPT, right? So I don't know if there was any diagram here. So here you have KKT, right? This part and this part, both of them are KKT, right? So this satisfies KKT. This also satisfies KKT. But graphically, one of them, which of them has to be the minimum, because f of x1 is x1 plus x2, right? So x1 plus x2 kind of increases like this. It increases in this direction. So the minimum has to be here. This has to be the optimum. So yeah, you can reason like that. So graphs can make you eliminate cases, unnecessary cases by intuition. Okay,
Okay, sir.
got it?
Sir, can you open ninth problem once?
Yeah.
So here, how can we find that after finding Hessian matrix, how can we conclude that whether X star is a minimizer or maximizer?
Can you conclude?
X star is a local minimum point or maximum point.
What are the eigenvalues at X star?
Okay, if eigenvalues ends up both mixed up, like positive and negative.
So the Hessian at 1, 1 is having both mixed up eigenvalues.
Yes, both positive and negative.
Then it can't be the minimum. I don't know. You might have made some mistake because the question C says show that the point 1, 1 is the only local minimizer, which means at 1, 1 the Hessian matrix at 1, 1 has to have both positive eigenvalues. So,
Sir,
Not
actually,
exactly
on
the same
this,
problem. Generally,
this
I'm
point,
asking.
yeah, on this
Ah.
point itself, no, the same thing which we were discussing at the initial level. If we have one positive and one negative eigenvalue, how to solve it? That only what sir was deriving it. We had to find the null space. So that only we wanted to discuss. I think that's the same question I also
Oh,
have.
see Hessian matrix with constraint or without any constraint?
With equality. So I have it now. I am sharing my screen.
Okay.
So this was the constraint problem there, where x1, x2 plus x2, x3 plus x1, x3 is the function, and x1 plus x2 plus x3 is equal to 0 is the constraint there. So delta Lagrange was found out, and then the eigenvalues, the double differentiation was taken out. The eigenvalues came out to be 2, -1 and 1. So sir said that it is not a feasible form. Okay, then I'm moving it forward.
So now with the constraint, okay.
So he said this. This is the statement which he will put it here. So he is finding the null space of Z.
Okay, so what's the null space of what?
The H function, that is the constraint condition, x1 plus x2 plus x3. So 1, 1, 1 comes out to
Okay,
be
what's the null space of that?
yeah.
Span
So
span
sir
of
has
this,
given
okay?
-1, 0, 1, -1, 1, 0 as the null space. Then finally he writes uh, check for the positive definite of the Hessian, the projected matrix. So Z transpose delta square H Z. So this is a projected Hessian matrix, and then he's saying if you can get the positive then it is means the
What he is saying is if you restrict the Hessian to the subspace spanned by those two vectors. Okay. And in that restriction to that subspace, it is turns out to be positive definite, then it's a minimum. Okay. Do you understand?
okay.
So the null space of Z is span of those two vectors -1, 0, 1, -1, 1, 0, right? It's a two-dimensional subspace, right? Okay.
Yes.
You can restrict the Hessian matrix to the two-dimensional subspace, right?
Hessian matrix.
Yeah, matrix A that takes one vector V and and gives another vector V. I can restrict the vector V to a subspace, right?
So means I am not able to understand. So Z transpose this Hessian matrix Z. We need to calculate it, and then we need to find the
So
eigenvalues.
what you do, okay, I'll tell you the exact procedure. Assume your vector is lambda 1 times -1, 0, 1 plus lambda 2 times -1, 1, 0. Write it. Can you write on your? Okay, you can't write. So I'll just orally maybe wait.
Maybe if you can write it on your screen, that is okay. Means the
I don't
problem
have
statement.
a proper writing thing. I can just open a Word document and then write that. Wait.
So once the mixed eigenvalues are coming, no, we are not.
I'll tell you, I got a question. I got a question. Plus, wait a minute. So I'll share my screen, okay?
Yes, please.
Uh, is it visible? So assume your
Yes.
vector V is, let's say, lambda 1. Wait, I can't write lambda here, so I'll have L1 here. Is it fine?
Okay.
L1 times what vector did you got? Minus 1, 1, 0, right?
Minus 1, 0, 1 is the Hessian vector you are asking about, or the null space vector?
The span of those two vectors.
Okay, it was minus 1, 0, 1, and the other value was minus 1, 1, 0.
So these are the two vectors, right? So the span of this will be, let's say, I'll call it maybe D1. D1 times minus 1, 0, 1 plus D2 times minus 1, 1, 0, right? Correct?
Okay.
So what do you get here if you add this? You have minus D1 minus D2. And then
D2
D2 and then
and minus D1.
then minus D1 or plus
Plus
D1?
D1. Plus D1.
Okay, yeah, plus D1.
So this is your vector V, right? Arbitrary vector. Now compute V transpose the Hessian into V. This.
Okay.
Okay, we compute this. V transpose HV. Okay, quadratic. You will get a quadratic expression. You will get a quadratic expression in terms of D1 and D2. Okay, you will get a quadratic expression in terms of D1 and D2. Okay.
Okay.
And then rearrange that. Rearrange that in this form. Okay. So rearrange that as D1, D2 times some matrix M times D1, D2 vertically. Got it? Rearrange this. Now this M will be a 2 by 2 matrix. Check whether this is positive definite or not. Okay. Got it?
Okay. Maybe trying to
Okay,
understand.
sir. Yeah, we need to solve one
So
problem.
what you do is you
Yes.
take V is D1 into something plus D2 into something. Substitute that into V transpose HV, where H is the Hessian. You'll get a quadratic expression in terms of D1 and D2. I'll just give you a random example. Let's say you get D1 square plus 5 D1 D2 plus D2 square. How can you rewrite this so you can simplify this. You can rewrite this as D1 square plus 2.5 D1 D2 plus 2.5 D2 D1 plus 1 D2 square. So here also you'll have 1. You can write this as D1 times D2 times a matrix 1, 2.5, 2.5, 1 times D1, D2. Like this you can write. Got it?
Okay.
So ultimately you'll get something times d1 square plus something times d1 d2 plus something times d2 square. Okay. I'm just assuming 1. These are all 1. If you want, I can write 2 or 3. So here it will be 2 and 3. And whatever you get for d1 and d2, you split up into 2 parts. If you get 5, you split up as 2.5 and 2.5 for d1, d2 and d2, d1. And then you can rewrite this as the matrix here will be now 2, 2.5, 2.5, 3. Correct? If you expand this, if you expand d1, d2 times 2, 2.5, 2.5, 3 times d1, d2, you will get this quadratic. Okay. Now this new M will be, now this 2 by 2 matrix M will be 2, 2.5, 2.5, 3.
So we calculate
Now
the
check,
eigenvalues of this.
let's check whether this eigenvalue of this guy M 2 by 2 matrix is both positive, then it will be a minimum. Even if one of them is negative, then it is not a minimum. Okay.
So we will
Got
not be
this?
able to say about the maximum, or we will be able to say something if
If
both
both
comes
of them are
negative.
negative, then it's a maximum. If both of them are negative, it's a maximum. If both of them are negative, it's the minimum. If it is mixed, then you can't say anything. It's a saddle. You throw it away, garbage. Okay.
Both are negative, that means it's a maxima, right?
Yeah. Both are negative maximum, both are positive minimum. If it's mixer, it's called a saddle point. It's neither maximum nor minimum. If like x1 square minus x2 square. In x1 direction, it's a minimum. In x2 direction, it's a maximum. So it is garbage, you know, and it's neither maximum nor minimum. Okay. Got this? So that's how you do it. You figure out, you write a general expansion based on a span, and then you substitute that general expression into the quadratic, Hessian quadratic, and then rearrange them in terms of the independent spanning variables to get a restricted Hessian matrix, which is this. And then check whether this is all positive or all negative or whatever. Okay. Got it? Got it? If you have any questions, you can email me here. Since I'm passed out of IITM, I don't have access to your Moodle page. You can email me here. Okay. Got it? You can email the other TAs also, and I'm just giving you my email ID in case. Okay. Any other question?
Sir, about the third question, we need to do Lagrangian function in that case.
Third question. Yeah, whatever we is unconstrained, right?
Yes.
Just find the gradient equal to 0, find the stationary points where gradient vanishes, and check the Hessian. If they are all positive, then it is. If it is no constraint, why are you doing Lagrangian?
Okay.
There's absolutely no constraint there, right? Why are you doing Lagrangian? Just check the gradient equal to 0 points. Find
And
the
those
Hessian.
points needs to be substituted in Hessian matrix.
Yeah. So those gradient equal to 0 point each of them, find the Hessian at each of them. If both are positive, minimum. If all of them are positive, it is minimum. If all of them are negative, it is maximum. Otherwise, it's a saddle point, neither maximum nor minimum. Okay.
Okay.
So yeah. So this is a general technique for finding Hessian for equality constraint problems. So find the null space, find the span of the null space. So write them in independent expansion. Okay, like d1 and d2. And then rewrite the quadratic for the Hessian in terms of d1 and d2 alone. And then you get a quadratic in terms of d1 and d2. Check the positive definiteness of that quadratic expression. Okay. Any quadratic can be expanded into a matrix. For example, if I take, I'll just give you a random example. If I have a matrix 2, 3, 2, 3, 3, 1. Okay, let's assume this is the matrix. And then here you have X and then Y. So you have this matrix. And then let's say you have, I just close this for clarity. Then you have, let's say, X, then Y. If you expand this, what will you get? Expand this, you will get
2x square,
x square plus
6xy.
3xy plus 3yx plus
Y square.
1y square, correct?
Yes.
Correct?
Yes.
So you know how to go from a Hessian to a quadratic. What I'm asking to do here is go from the quadratic to the Hessian. If somebody gives you this quadratic, if somebody gives you the quadratic 2x square plus 6xy plus 1y square, then the first step you need to do is symmetrize the xy form. Write 6xy as 3xy and then 3yx. So if you have any other expression in a quadratic, write, for example, 5xz as 2.5 xz plus 2.5 zx. If you do that, you will get something like this. And then once you do this, you can just intuitively write down the matrix. The x square coefficient will be the xx entry. The y square coefficient 1 will be the yy entry. The xy coefficient 3 will give you the xy entry. The yx coefficient 3, they have to be the same because symmetric matrix you will get here. Okay. So you can convert quadratic expressions to a Hessian matrix, and the Hessian matrix, if you expand quadratically, you will get a quadratic expression. Okay. Got it? You can do this for 3 by 3 quadratics also. You know, x square, y square, z square, xy, yz, zx. So split xy as xy plus yx, split yz as half of yz plus half of zy, split xz as half of xz plus half of zx, and then you will have, if you have the quadratic matrix, you will have the x square coefficient here, and then you will have xy, xz, and then at the next entry you will have the coefficients of 1, 1, 2, 1, 3, 2, 1, which is yx, yy, which is y square, and then yz. And then the next part, the next entry will be zx, zy, and then zz will be z square. Got this? So this is how a matrix is built. Okay. Got it? For a 3 by 3 case, 3 quadratics. For a 2 quadratic, you will have just x square, xy and yx for off diagonals, and then y square at the bottom. Okay. Got it? I think its meeting is going to end soon. So this is my email ID for future reference, this one. So if you have any specific doubts, you can email me. So I guess that's it then. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.